Swayam Prabha. Digital India. Educated India.
Okay, so now let's start getting our hands a little bit dirty in constructing these, constructing cryptography from these ideas. So, the most basic thing that you would want to construct, of course, is a one-way function, right? And we have seen these in the context of RSA, discrete log and so on, right? Easy to compute, hard to invert. This is the most basic primitive in cryptography. So, let's try to construct two different one-way functions using the ideas that we have seen. So, in the first example, this was this one-way function was suggested by IIT, back in the early 90s, and this is how you define it. So, you are taking you sample a random matrix A, okay. This matrix is n cross m with m satisfying this relation. So, m is greater than n log q, q is the modulus for A, okay. So, I am sampling A from ZQ, okay, and it is a fat matrix. So, it is from ZQ n by m, uniformly random, and great. So, I am going to use this matrix to define my function. So, I am going to simply define my function as A times x. So, what is the domain of my function? It is actually the set of all binary vectors. So, you can generalize this to low norm vectors, but maybe for simplicity it is good to think of just binary for starters. So, I am going to define my function as going from binary vectors of dimension m to vectors over ZQ of dimension n. Okay, so, A is n by m. So, Ax is going to be n by 1, right, and the domain is 0 1 binary, right, 0 1 to the m, and the range is ZQ to the n. Okay. So, very good. So, can you first of all, the function is very easy, right, just I have a matrix, you give me an input, I just do matrix times input. It is a very, very easy function. Now, why should this be hard at all? I mean, given A, right, if I give you A, so let me ask here, why is this hard to invert? So, what does it mean for a function to be hard to invert? I am given A and I am given some Ax, let me call that y. Okay, what is my goal? It is to find x. This is what it will mean to invert this one-way function, isn't it? You can see that I am claiming something very strong, right. I am saying that if you could invert this function, this matrix vector product, I am saying you could find approximate solutions to a shortest integer vector problem in the worst case, not even in the average case, but on some kind of worst case lattice you can solve this problem. I am claiming such a strong thing. Why is that? So, why can't I just do Gaussian elimination and solve for x? Okay, it is because of this. So, the domain of my function, right, is 0 1 to the m to ZQ to the n. If I do Gaussian elimination and find some x using that, it will be over ZQ, it will be ZQ to the M. Now try to intuit what is the connection with the problems we have seen before. This X needs to be low norm, it needs to be a short vector. So what I am asking for is actually a short vector in a lattice, finding any vector to satisfy this relation. So satisfying this relation basically just means that I have to be in this lattice, okay. And finding a binary vector means that it has to be a short vector. So this will be a question of finding a short vector in a given lattice, and that is why it will be hard, okay. So this is the first one-way function. Then there is another one-way function which was defined by Regev in 2005. So in this, once again I am taking this random matrix A, but now what I do is, instead of multiplying a vector like the input on the long side, I multiply on the short side. So previously I had my vector x as being multiplied on the long side of the matrix, and I had x being binary. Now I choose my vector to be over ZQ itself. So this is not binary anymore, this is over ZQ, and I multiply it on the short side. So now if I just give you A times S, can that be one way? So I am now defining a new function G sub A, okay. I take as input this this vector S, which is over ZQ to the K, right, and I multiply S with A on the short side of A, okay. So AS, can this be a one-way function? Is it hard for me to compute S? It's not a trick question, it's easy, right, by what we discussed. So to make it hard, I will perturb it with some noise, okay. So what do I mean by that? Now what I will do is, I will compute AS, but I will add to it a vector E of low norm, okay. Again, for simplicity you can think of E as binary, even though we will actually, it can come from more general distributions. For simplicity, just think of it as binary for now maybe. So I am defining my function G sub A as taking S from ZQ to the K and E from some some distribution, some low norm distribution, right. And like I said, for simplicity you can just think of this as binary, okay. And I define my GA of S comma E as AS plus E mod Q. So the learning with errors problem is that now I will give you A and I will give you this GA of SE, and I want to find S. So note that without the E, this problem is trivial to solve. It is an over-defined system of equations. So it can admit only one solution, and moreover that solution is not even low norm. So it is easy for me to find that solution. So the surprising thing here is that if I simply perturb this with some random noise, okay, let us say that I flip coins. If it's head, I add 0, if it's tails, I add 1, for example, right. The claim here is that if I simply perturb this with some random noise, then I cannot solve it. Now what is the naive algorithm that comes to your mind for solving this problem? What is the problem we are solving? Given this AS plus E, I want to recover S. And I know that without the E it is trivial to solve, right. So, what is the naive idea for solving this problem? Thing is, I have given you A and I have given you some Y which is AS plus E, and as usual I will give you these dimensions, right, these are given, and what I want is S. So, can anyone suggest algorithms for solving S, finding S? So, let us be careful. So, let me repeat the suggestion for the class. The suggestion is that I know the distribution of E. So, maybe I can try out many different E's and see. And you were saying that I'll try and see if it matches, but note that this is my input, I only have A and Y. So, matches what? So, basically what I would be reduced to doing is I would need to guess the E, subtract it from Y and then try to solve for S, right. Now, this is an overdefined system. So, if there exists a solution, I will find it. So, I can try this. So, how much time does this take? It is 2 to the m, right, because I mean how will I guess the E? So, it does not work, but I mean it is not supposed to work, it is a one way function, right. So, indeed, so this is this problem is this is a really fantastic problem. I mean both of these, yeah, we will see very little about them in this course. Anyway, so the theorem is that this function is hard to invert on the average, assuming that SIVP is hard to approximate in the worst case. Okay, so this is a very strong statement. So, what this is saying that if for a random A, so hard to invert on the average, right. So, that means that if I sample a random A, okay, and I have an oracle to solve this problem. So, I for a randomly sampled A, if there is an oracle which given GA of SE gives me back S, then that S allows me to actually solve the shortest integer vectors problem in the worst case, an approximate version of the SIVP problem in the worst case. So, it is a very strong worst case average case guarantee. If I have a oracle to solve an average case problem, like only a random instance of a problem. Note that solving a problem in the worst case means that any instance I can solve. Solving in average case is much weaker, right, because it is saying that only for some well distributed inputs I can solve it. So, when I pick things randomly, right, the distribution, I mean intuitively you can think that when I am picking things randomly, I am likely to avoid the bad cases intuitively, right. So, it is being able to solve something on average or for random instances is much weaker qualitatively than solving something in the worst case, and this is saying that I will solve SIVP in the worst case if you give me a way to solve to invert this function only in the average case. So, it is a very strong guarantee. Okay. So, now since we are running out of time, let me just let me at least conclude this part of the discussion by summarizing the two one-way functions that we saw. Okay. So, one of them, the first one, this is IITs, right. In this we have this function AX mod Q. We will go over the rest of the stuff in the slide in just a moment. I just want to do a quick recap before we proceed. And the second function that we have, this is regevs, Okay, this is AS plus E mod Q, okay, where S is multiplied on the short side, it is from the whole space, and E is binary. Okay. So, these are the two one-way functions. Now, it turns out that these are one-way functions, right, but it is not enough for us to get more useful primitives like public key encryption and signatures. Okay. So, what we will now do is we will sort of use the intuition we have built from the one-way functions that we saw to define two new problems on lattices, and we will use those problems to actually construct some more useful cryptography. Okay. So, in general, note that when I have one-way functions, one-way functions do not imply public key encryption. Okay. So, to get public key encryption, I have to do something more than just use a one-way function. So, let's look at how to get public key encryption and digital signatures. So, let's look at the first one-way function that we saw, okay, and try to abstract out a problem from that. So, we will define this short integer solution problem. This was at the heart of the first one-way function we saw. So, here we are given this random matrix A from Z q n by m, okay, and q is some polynomial in n, and m is greater than n log q. We saw these conditions earlier. And the short integer solution problem, which as I said is at the heart of the first one-way function, is the question of finding a low norm vector x such that it hits the Ax that I am given. In the case of the short integer solution problem, I will just ask it to hit a particular point 0. But this problem is meaningful even if I replace 0 with some other arbitrary point y. Even in that case this problem is meaningful. But for the sake of defining this problem, we will just try to hit 0. So, the question is I am given this A and I am asking you to find a short x such that A times x is 0 mod q. Okay. So, it is a short integer solution, right, that I am after. So, it needs to be short. So, here we will not necessarily ask for x to be binary. Let us say that we just want the norm of x to be less than some beta that I give you, okay. And so, I want x to be integral. So, that is why I want a short integer solution. This is the short integer solution problem. And from the second one-way function, intuited by the second one-way function that we saw, is this learning with errors problem. Okay. So, remember that we saw that we want to generate our function output as As plus E, right. So, As plus E is like if I think of each row of A, As plus E is the inner product of the row with S plus noise, right. So, that is what we have on the left side here. This noise is again, it is coming from some low norm distribution, which for the moment I will not specify. Okay. So, I am generating this As plus E in this way. I will sample S at random, okay, from the whole space of the appropriate dimension, the short side of the matrix, and I will sample this error from some low norm distribution. Think of binary for simplicity again, and I will compute these noisy inner products. The learning with errors problem says that not only is it hard to recover S from this these samples, but moreover in fact I cannot distinguish these points from uniform points in the whole space. So, on the right side, if I just have the uniform distribution of the appropriate dimension, A is already given. So, we are only trying to figure out whether this vector AS plus E, this vector which we are calling B, is this vector computed as AS plus E or is it uniformly random? Okay. So, the learning with errors problem is simply to distinguish between the left side noisy inner product distribution and the right side uniform distribution. I am not even asking you to solve for S. It turns out actually that you can show that the search and decision problem can be reduced to each other. So, of course, you know, if you can solve the search problem, you can certainly solve the decision problem. But even the other way around holds. If you can solve the decision problem, turns out you can also solve the search problem. Possibly we might see this in our homework. Okay, so this is the learning with errors problem. And now using SIS and LWE, so short integer solution and learning with errors, you can compare these two one-way functions that we saw. Okay. So, the first one was, you know, just AX mod Q. So, here X is short, okay, and this one way function is surjective, right. So, this is the output space is ZQ to the n is the shorter side of the matrix. Okay, this function is surjective, and you can show that if the short integer solution problem is hard, then actually this function is not only one way, it is a collision resistant hash function. Now, we did not really study them in this course and we will not, but I will just you know, so I will just say one line about it. I mean it's a hash function, I mean it's, you know, compressing the input. It is taking m and sort of hashing it down to some n, right, and it is collision resistant. So, it is not only is it hard to invert, it's also hard to find two points that map to the same output. Okay, so this was our first one way function. The second one was, you know, AS plus E, or in this notation S transpose A transpose plus E transpose. This in this the S is actually large, but the E is not only short but very short. Okay, so yeah, I apologize for waving my hands around these things. We don't have time to really delve too much into this, but yeah, this function is injective. Okay. So, given an output, there is only one input. So, with the first one way function, you know, there could be many possible x's that map to the same y, but it is collision resistant, it is hard to find them. There are many that will map to it, but it is hard to find. The second one, it is actually injective. The E is so small that actually there is only one value for E and only one value for S given a y. There are not many values. Okay, so, it is injective, and this is a one way function if LWE is hard. So, it turns out that these two problems, SIS and LWE, not only do they give us these one way functions and whatever CRHF in the case of SIS, they give us all kinds of really cool cryptographic primitives. The first one gives us digital signatures. The second one gives us public key encryption, and in fact both of them give homomorphic versions of their respective primitives. So, for SIS you can get homomorphic signatures, for LWE you can get homomorphic encryption. What homomorphism means is that you know, I can compute on these signatures or these ciphertexts. So, I can add signatures, multiply signatures in a way that you know, it remains faithful to the same function applied on the messages. Similarly, for encryption, I can add ciphertexts and multiply ciphertexts in such a way that when I decrypt, I get you know, the same computation applied on the message. So, these are things that we in fact do not know from any of the pre-quantum assumptions either, and my hope is to show you at least one of these, probably the encryption, because it is more, it's simpler to describe. Okay, so let's stop here for today. We'll continue tomorrow with how to build these things. Thank you.